Hello there people, what's up? Today we're talking about a way to do function level caching. Suppose you have a long running or slow function and you call it over and over again in your code. So you want to cache the results in order to memorize what you already calculated. Should the function be called again with a parameter that it has already been called with before, it should not calculate the result again, it should rather return the cached value. Now, while this idea is very simple, I'm going to show you a decent way to do this while having the code that contains the caching logic separated in its own building block, which means the caching logic is put into a separate function. So if you want to apply this mechanism to multiple of your functions, this can be done very easily. This only works in programming languages that support both closures and functions that can return other functions. This is possible, for example, in Lisp or in JavaScript. We're going to do this in JavaScript now. Memoization is a technique that is around since the late 60s, and it is heavily in use by the Lisp community. Although memoization is mentioned in a couple of very good JavaScript books, I don't see memoization in use too often in real-life code. So I hope that with this video you can learn something new, and maybe you can even use this technique in your code in the future. Okay, so I have here my slow function, okay. It just calculates stuff over and over and over again. It's not really important what it does. It returns 6 plus this value here. So if we call slow fun of 100,000, it returns the value of 100,006. And this takes about 3 seconds on my machine. I already tried this out. So now we are going to implement our caching logic, and we could implement this inside slow fun, okay, but this is not what we want. We want to separate the caching logic from everything else, okay, so we can apply the caching logic to multiple functions and not just to one function, okay. So I'm going to write a separate function that contains the caching logic. And here we're going to use some features that are not available in every programming language. So first of all, I'm going to make a function memorizer, and this function gets another function as a parameter, okay? This is the first thing that is not available in every language. We are having a function that has a parameter, and this parameter is another function, okay, and the memorizer should return a function that is like a cached version of this function, okay. So let's see, I'm going to first have a variable, an array that acts as a cache. So I'm gonna have a cache here that is just an array, okay. And the function returns another function that has one parameter, namely n, and don't forget the semicolon here, and the function that should be returned should be like a version of the original function fun that is capable of caching, okay. So that's the main idea. Because I want an associative array, I'm gonna convert this parameter n into a string, okay? So I'm gonna have an index variable, and this is just n.toString, okay? Just to make sure that I'm working with strings here. So now I'm going to check if cache already contains a value for this index, okay? And if it does not, if it is undefined, I'm going to calculate it. I'm just going to calculate it. So I'm going to say cache of IDX is fun of n, okay? I'm calling this parameter here with the value of n, and I'm storing its result in the cache, okay? And after this code, I'm sure that cache of IDX contains the return value of the function call of n. So all I need is just to return the cached value. Okay, there's a lot of strange things going on here that are not available in every programming language. Okay, we are having a function as a parameter, we are having a function as a return value or return function, and we access a cache that is defined outside the function we're using it in. Okay, so this is done by closures. Okay, so now I'm going to show you how this works. Now I'm going to have a variable memSlowFun. Okay, and this function or in this variable we just store this function here. Okay, so it's memorizer of slowFun. Okay, and now in this variable we have a version of slowFun that is capable of caching. All right, so if we measure the time it takes for slowFun, it should be 3 seconds. If we measure the time it takes for memSlowFun, it should also be 3 seconds because it's the first call. But if we measure the time again with memSlowFun, it should be very fast, like 0 seconds. All right. So let's try it out. Save and let's load file. It should take about, I don't know, 6 seconds to see the results. Okay, and here we are. So the first call was the call of slowFun. Second call was the call of memSlowFun. And the third call was the call of memSlowFun again. And you see here that it prints out the correct result, and the execution time is actually it's a little bit more than 0 seconds, of course, but it's too less to be shown here. So this was pretty fast, right? I'm going to show you now what you also can do is you can actually overwrite. You can overwrite the definition of slowFun with memorizer of slowFun. Now I'm just showing you what's technically possible. All right. If you decide to do that, I would recommend you to put this line very close to where you define your function. Okay, because what you are doing here is you are changing the behavior of this function, and if you do it somewhere in the code, it would not be clear what's going on. Okay, so this is just a demonstration of what is technically possible. You can do something like this, and now we have overridden slowFun with the fast one, with the memorization version. So let's try it out. Load file, and here we are. This is the first call of slowFun. This is the second call of slowFun. Okay, so I have one more example for you. So we're going to make a function fib of n that calculates the nth Fibonacci number. We're going to do this in a very non-performant way. So if n is equal to 1, we return 0. If n is equal to 2, we're going to return 1. And otherwise, we're going to return the sum of the two preceding numbers. All right. And this is a slow executing function because there's lots of redundant computation going on here. So in order to calculate, for example, the fifth Fibonacci number, we're going to calculate the fourth and the third Fibonacci number. Now, to calculate the fourth Fibonacci number, we are going to calculate the third Fibonacci number again, and then the second Fibonacci number. In order to calculate the third Fibonacci number, we're going to calculate the second Fibonacci number again, and so on and so forth. So this is what we call redundant computation. There's lots of redundant computation going on here, so that's why this function is slow. If you want to know more about the Fibonacci numbers and how to write a better function, a more performant function, you can watch my video on the Fibonacci numbers. But for now, let's see how long it takes, for example, to calculate the 43rd Fibonacci number. All right, let's see. And it takes 2.2 seconds, all right, or rather 2.3. And let's see. Well, we have redundant computation going on here. So actually, if we make a cached version of fib by doing this, we suddenly get rid of this random computation, not random, but redundant computation. All right. So the calculation of fib of 43 should be way faster now than 2.3 seconds. So let's try it out. Okay, so here we are. 0.001 seconds. All right, let's try it out again. Okay, let's delete it, try it out again. Okay, it doesn't change. Even 0 seconds, so it's beyond range. Okay, if you are new to concepts like closures or functions that have functions as parameters and return other functions, just search the internet for tutorials on these topics, or feel free to leave a comment if I should do a video about some of these techniques that are going on here. Alright, so have fun, happy coding, and see you next time.